Bohr model of the hydrogen atom. Bohr combined classical and early quantum concepts and gave his theory in the form of three postulates. These are: Bohr's first postulate. In an atom, the electrons revolve around the nucleus in certain stable circular orbits or shells without the emission of radiant energy. Each shell or orbit corresponds to a definite energy. Therefore, these circular orbits are also known as energy levels or energy shells. Bohr's second postulate. Bohr's second postulate states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h upon 2 pi, where h is the Planck's constant, is equal to 6.6 into 10 raised to power minus 34 Js. Thus, the angular momentum L of the orbiting electron is quantized. That is, L is equal to nh upon 2 pi, equation 1, since electrons can be present only in these orbits. Hence, these electrons can only have energies corresponding to these energy levels. That is, electrons in an atom can have only certain permissible energies. Bohr's third postulate. Bohr's third postulate states that an electron might make a transition from one of its permissible non-radiating orbits to another of lower energy by losing the energy equal to the energy difference between the initial and final states. The frequency of the emitted photon is then given by h nu is equal to EI minus EF, equation 2. Similarly, if an electron present in an atom can move from a lower energy level, E lower, to a level of higher energy, E higher, by absorbing the appropriate energy, the energy absorbed is equal to the difference between the energies of the two energy levels. That is, delta E is equal to E higher minus E lower. Bohr's second postulate of quantization, equation 1, says that the allowed values of angular momentum are integral multiples of h by 2 pi. Ln is equal to m Vn Rn is equal to nh upon 2 pi, equation 3. Rn is the radius of nth possible orbit and Vn is the speed of moving electron in the nth orbit. N is called the principal quantum number of the orbit. Using relation R is equal to E square upon 4 pi epsilon naught mv square, equation 4, we get the relation between Vn and Rn as Vn is equal to E upon under root 4 pi epsilon naught mRn. Combining equation 3 and equation 4, we get Vn whole square is equal to E square upon 4 pi epsilon naught into Vn upon nh upon 2 pi. Vn is equal to 1 upon n E square upon 4 pi epsilon naught 1 upon h upon 2 pi, equation 5, and Rn is equal to n square upon m h upon 2 pi whole square, 4 pi epsilon naught upon e square is equal to n square upon m h square epsilon naught upon pi e square. Equation 6. Equation 5 shows that the orbital speed in the nth orbit decreases by a factor of n, Vn proportional to 1 upon n. Using equation 6, let us find the size of the innermost orbit n is equal to 1. R1 is equal to h square epsilon naught upon pi me square, equation 7. This is called the Bohr radius, represented by the symbol A0. Thus, A0 is equal to h square epsilon naught upon pi me square. The total energy of the electron in nth orbit of the hydrogen atom, En is equal to K plus U is equal to minus E square upon 8 pi epsilon naught Rn is equal to minus E square upon 8 pi epsilon naught into m upon epsilon naught n square h square pi e square. En is equal to me raised to power 4 upon 8 n square epsilon naught square h square. Equation 8. Substituting values, we get En is equal to minus 2.18 into 10 raised to power minus 18 upon n square j. Equation 9. Expressing En in electron volts eV, we have En is equal to minus 13.6 upon n square eV. Equation 10. The negative sign of the total energy of an electron indicates that energy will be required to remove the electron from the hydrogen atom to a distance infinitely far away from its nucleus. Energy levels. The energy of a hydrogen atom in the ground state is the least, largest negative value. Its electron then revolves in an orbit closest to the nucleus. The energy of the electron in the ground state of the hydrogen atom, n is equal to 1, E1 is minus 13.6 eV. Therefore, the minimum energy required to free the electron from the ground state of the hydrogen atom is 13.6 eV. Therefore, the ionization energy of the hydrogen atom is 13.6 eV. Thus, as n increases, the value of minimum energy required to free the electron from the excited atom decreases. Atom is said to be in an excited state when the electron is raised to higher energy states. For n is equal to 2, the energy E2 is minus 3.40 eV. It means that the energy required to excite an electron in hydrogen atom from its ground state, n is equal to 1, to its first excited state is equal to E2 minus E1 is equal to minus 3.40 eV minus 13.6 eV is equal to 10.2 eV. Similarly, to excite the hydrogen atom from its ground state, N is equal to 1, to second excited state, N is equal to 3, 12.09 eV energy is required, and so on. The farther the electron is from the nucleus, the more energy it has. From these excited states, when the electron falls back to a state of lower energy, it gives out energy in the form of radiation. The energy of the light emitted or absorbed is exactly equal to the difference between the energies of the orbits. As the excitation of hydrogen atom increases, the value of minimum energy required to free the electron from the excited atom decreases. Farther the electron is from the nucleus, easier it is to free it from the atom. The energy level diagram for the stationary states of a hydrogen atom is shown. The principal quantum number n labels the stationary states in the ascending order of energy. In this diagram, the highest energy state corresponds to n is equal to infinity and has an energy of 0 eV. This is the energy of the atom when the electron is completely removed. R is equal to infinity from the atom and is at rest.